Hello everyone, my name is Manmohan Mandan and welcome to my YouTube channel. Uh, so, I would like to discuss today's problem of the day, which is minimum flips to make A or B equal to C. It's a question from bit manipulation. The question says, given three positive numbers A, B, and C, return the minimum flips required in some bits of A and B to make A or B, A bitwise or B equal to C. So flip operation basically means we can flip any bit like from 1 to 0 or 0 to 1, and this will take a one operation. In one operation I can flip the bit from 1 to 0 or 0 to 1, and we want to convert. We want to make A or B is equal to C in minimum number of operations. Okay, so I would like to take you through this one note. So here, for an example, if my A is 1011, which is basically 11 in decimal, and suppose my B is 12 1100, and I want to make their or equal to C. A or B should be equal to C. I want to achieve this equation. Uh, suppose my C is 1001 here. Okay, let's take this one. Yes. So if I want to achieve this, I need that like at least one of these, this is the zeroth position, this is the first position, this is the second position, and this is the third position. So for achieving their or value equal to this, we want that there at least one of A's or B's zeroth bit should be set, and none of A's and B should not be set for this first position. Same for the second, and at least one of their bits should be set for the third position. Uh, okay, let me clarify first that what is A or B. A or B basically means if we are doing uh, suppose this, what is bitwise OR operation. If any one of them, at least like it's an option, any one of them is one, then our answer will be one. Only case, okay, sorry, my mistake. Only case when the both bits are zero, then only their bitwise OR will give us zero. uh, Otherwise it will give me one. It will give me a set bit, like one of the bits should be set, so it will give me a set bit. So for getting a one here, we want that at least A's zero bit or B's zeroth bit should be set. And here we can see A's zeroth bit is set, so we don't need any kind of operations here. And similarly for third bit, we don't need any kind of operation here. But here on the first position, A's first bit is set, and if uh, we perform an OR operation here, we'll get this first position as a set bit. But we don't want because second bit of sorry the first bit of C is unset, so we want to make this first bit of A unset. So for that we'll need one operation. So we'll set this sorry we'll unset this, we'll toggle this bit. So now their OR operation will give us 0. And similarly we need 0 on the second bit of C, but we can see here like is second bit, like second bit for both of the numbers are set here. So we'll need more two operations to unset these two bits. So our so the our OR operation will give us 0. So in total we'll need 3 bits, 3 operations. We'll need to change three we'll need 3 bits for getting our answer equal to C. So what are the two cases we have seen? That if we want 0 at any ith index, that ith index of A and ith index of B should be set. Both should be unset. So if this is set, we'll need one operation. If this is set, we'll need one more operation. And the second part is like if we need one on any ith bit, like any one of of the two numbers should contain a set bit on the ith position. And like if both has a unset bit on that ith position, so we'll need at least one operation to flip a bit in either A or B. It doesn't matter actually, we just need to report the number of operations. So we'll need one operation for in this case, and either one or two operations in this case depending on the case. So now there can be some cases where A has only 2 bits, like A's rightmost bit is still only first position, and there can be cases when B's so rightmost bit is still fourth position, or maybe they can vary. So for the sake of convenience, we'll take until unless the all A, B, and C gets 0. Till then, we'll continue our operation. So we'll take first an answer variable, and then uh, we'll check. We'll start checking from the 0th position to the position until all three gets 0. So what we will do, we'll first check the ith bit of C. If it's set, there are two cases. Maybe it's either it will be set or it will be unset. So if ith bit of C will be set, would be set, then we'll check whether A's ith bit is set or not, and B's ith bit or B's ith bit is set or not. If any one of two are already containing a set bit, we don't need any kind of operation here. But in case they both contain an unset bit at that ith position, we'll increment our answer variable by a value of 1. And in the next case, if there is an unset bit on the ith position of C, so for this we our condition is both ith bit of both the numbers is A and B should be unset. And if A- A's ith bit of A is set, then we'll increment our answer variable by 1. and if ith bit of b is also set, we'll increase our answer variable by 1. So only these three cases we need to handle. Now there's exists some like basic bit operations, like how we can check the ith bit. So we are like traversing it from back. We'll just and take a bitwise, and we'll take bitwise and with the numbers, the last bit. Basically what bitwise and do, it just gives a non-zero number if our like last bit contains a 1. Then this 1 and 1 gives a non-zero number. And if the last bit of any like the zeroth bit of any number contains a 0, then 1 and 0 gives our result as 0. So we'll just check, we'll just do 1 and the number, suppose x, and if this gives a non-zero number, then we can conclude that x is like x contains a set bit on its zeroth position, similar, and vice versa. If it gives us 0, then we can conclude that x contains at unset bit on the zeroth position. uh, so here is the code. You can see like the similar thing I have did, and after every operation, after checking this, we'll right shift all the three variables by 1. Basically we are dividing it by 2. We're doing right shift by 1 or dividing by 2 is the same operation. And why are we shifting it by a one position? Because we need to traverse through all the bits, so we are just taking the zeroth bit, and after checking it we are removing it. So now are the I minus 1th sorry, the first index, the I plus 1th index becomes ith index. So now first bit will become 0th bit, and we can check until all three becomes 0. So we need to right shift a, b and c, all the three variables by 1. So this is my code for this question. As I discussed, I just checked all three variables. I have taken three Boolean variables here. So this condition shows that if C contains a set bit on its zeroth position, P will be true, and similar for Q and R for corresponding B and A. So this condition is checking that if C's zeroth bit is set and they both are unset, so I will need one operation. And if P is unset, C does not want any set bit there, and Q and R, any one of them are containing a set bit. So I'll just if Q contains a set bit, I'll increase my answer by 1, and similarly for R. And at the end, I'll just right shift all the three variables by one position. So this is my code, and it gave me 100% on the time runtime morning. Okay, it's now 40%. I don't know why, but it gave me 100% anyways. So this was my code. Thank you for watching my video. We'll return with one more POTD. Good night.